Hello, this is my implementation of the Nand2Tetris computer, or the 16-bit hack computer in the Desmos graphing calculator. So, as with the Nand2Tetris course, we start with NAND. The NAND gate is implemented using Desmos conditional operators. Desmos conditional operators work similar to cons in Racket, where the condition goes first, and then the true case followed by the false case. So here you can see that is how I have composed NAND. From NAND, I then built out all of our basic logic gates to work with: NOT, AND, OR, NOR, XOR. And then the actual hack computer doesn't have this gate, but I wanted to implement XNOR. I believe I do use it at some point in the project. And then there's also MUX here and DMUX for control flow. One thing you'll notice that gets progressively annoying is that in Desmos, variable names or function names cannot have more than one letter, except for subscripts and superscripts. So all of my variables and functions are named in this weird, annoying to read way, where the first letter is big and then all following letters are small. Implementing the 16-bit gates is a simple application of the 1-bit gate 16 times. I've noted here that I do use the Desmos for function, which is not building stuff out of the gates, but it is truly a syntactic sugar for typing all of these individually for each I equals 1 to 16. So I did cheat there, I guess, but it would have just been very annoying to have to type out and A1, B1, and A2, B2, and, all of that. The multi-way gates are composed similarly from their single-way counterparts, namely OR 8-way, OR 16-way, MUX 4-way 16, MUX 8-way 16, DMUX 4-way, and DMUX 8-way. Neither OR 16-way nor DMUX 8-way actually exist in the original hack instruction set, but again, I've taken liberties to implement some of my own gates. Now, for the absolute monstrosity that is our ALU code, we start with the half adder, which is a simple AND and XOR. Then implement the full adder in terms of half adder to be capable of adding 3 bits, like so, and you can see the result in the bottom right-hand corner of the text box where I'm typing the expression. So you can see our adder is functional. I don't even want to explain everything that's going on in the add16 implementation, but it's effectively a recursive way to do the same thing that I did with the 16-bit gates of hacking together, typing the same thing 16 times. Recursion is technically not using our logic gates once more, but again, this is where I take a liberty with how I'm expressing it for the sake of, me not going insane as a programmer. With add16 implemented, inc16 is very easy, and I have my 0if and negif as helper functions for the ALU, which just zero and negate their inputs based on a selector bit. Compute simply does the ALU's job of applying either bitwise AND to its inputs or adding them together. And it of course does this based on whether the add flag is 1 or 0. With all those helper functions made, the ALU is actually quite nice to look at. We negate and 0 our x if we should. We negate and 0 our y if we should. We execute the selected operation on them, and we negate our output if we should. Finally, the helper function zrng just tells us if our ALU output is 0 and if it's negative, and this is as with the zr and ng outputs in the actual hack implementation. The RAM is yet another place where I deviate from the official hack spec due to the limitations of Desmos. In Desmos, lists can be no more than 10,000 elements, so I have the RAM of my implementation of this computer as 4 8192-bit chunks, so that's actually only 2,048 16-bit words. Mem3 and Mem4, which is words number 1025 to 2048, correspond to the screen memory, which is rendered over here in the actual Desmos graphing calculator in this little square region I have here. That is a 128 by 128 pixel region. You may be wondering why the screen memory starts at 1025 instead of 1024. That's because Desmos arrays are not 0 indexed, they are 1 indexed. That means if we have an array called R, our index 1 will correspond to the first, or traditionally 0th, element of that list. And if you're wondering, no, I did not individually type out all of these zeros. Once again, for loops have come to the rescue. Using something like this, I composed all of the memories, and then writing to them via actions, which I'll get into later, separates them out into these actual individual zeros. In terms of my code for writing to the RAM, which we never actually had to handle when doing the Nand2Tetris project, it was always handled by the emulator or the system. In this case, I actually have to make the formula for, given a specific machine word, how are we calculating the offset to set a specific bit, and then do that for all the registers so that given any specific address, we can just set the RAM at that address. So that's all these implementations here, set mem3, set mem4. There's possibly a cleaner way to do it, but this is what I came up with that worked. The ROM is implemented in the exact same way, in this case being two 8192-bit chunks, ROM1 and ROM2 respectively. When a program is loaded, ROM1 fills out first, and then ROM2 until they're both full. As well, we have our A, D, and M registers. A starts at pointing at address 1. Again, remember, because Desmos is 1 indexed, so our array at address 1 is going to be the first machine word. And M is the 16-bit chunk at whatever the current address is. If I change that, if M was different anywhere, M would change. The CPU is another absolute monstrosity of a function. Simply because I could think of no better way to do this. We've broken it down into a few helper functions, but it's still pretty gnarly. To start, ALUI just applies the ALU to a set of instructions, so it calls it with whatever's in the D register, and then either the A or the M, based on that A bit that you'll remember, which selects whether we use the A value or the M value, and then it passes to it all these instruction bits in the correct order. As well, should jump takes the ZRNG from the ALU output and the instructions and determines whether or not we should jump at the current instruction. Because the ALU output is used so many times throughout the CPU function, I've actually split these into two separate functions where the ALU output is passed to CPU impl, short for implementation. This is just to avoid recomputing the entire ALU function every time that I need that ALU output within the CPU. So the actual implementation of the CPU sets the A if it should, sets the D if it should, sets the M if it should, increments the program counter how it should, and also passes whether or not it should jump based on the ALU output. And it's actually amazingly that simple. I use a little Desmos trick called with here. It is similar to let bindings in Racket, where you can make a temporary name that just exists for this expression. So I do that to avoid having to retype the ZRNG function over and over, and this also does cache that value in the same way. This function here, tick, just executes the 16-bit instruction at the current program counter's address, passing that on to the CPU. I built this test suite for some of the earlier stages of the process. The actual memory mucking stuff is too complicated to test with this simple check expect strategy, but it was useful for the ALU as well as all the logical things. So let's test my code with the actual Nand2Tetris assembler by translating this brief program that I've written to fill the screen with black by repeatedly setting each 16-bit chunk to 2's complement of -1, which is all 1s, which is all black. We can see if my Desmos computer is truly compliant with a simple program like this. With a quick jaunt to my favorite website ever, regex101, we can get this output as a nicely formatted list. By then pasting this into Desmos, we can create a program called fill, which, by loading that into our program memory and beginning the execution, we'll see the screen begin to fill up with black, albeit quite slowly. You can see our A, D, and M registers, as well as the program counter and whatever the current instruction at the program counter is, i.e. whatever's being executed. It fills up incredibly slowly because Desmos is not designed to be a 16-bit computer, but if I let this run for a while, And I do mean a long time.
One eternity later.
You can actually see the full screen fill up. It just does take a long, long, long time for any instructions to execute. So yeah, that was this project. I had an absolute blast doing it on the Amtrak on the way to and from visiting my sister in New York. Thank you for the attention that you've given this video. Bye!